Okay, so back to our question that we were trying to finish up here. We're trying to calculate the average atomic mass for neon. And so we set up the problem. And so now we just have to add up the products of the fractional abundance divided by 100 times the atomic mass for each isotope. And so here, notice I wrote out all the numbers that my calculator would give me. And then I wrote it out here, and then I'm going to trim it off. And so generally, depending on how many decimal places they're wanting, and technically your question doesn't specify, but generally that's 2 or 3 or even 4. So if you notice on your periodic table, sometimes you have average atomic masses that have 2 decimal places. Sometimes they have 3. Sometimes they have 4. What's the difference? Well, whatever method they used, the values that have larger number of decimal places just means that the instrumentation that they used had a more precise way of measuring the values. Okay, so let's go back to our PowerPoint, and then we're going to look at the next calculation here. And it's actually, I'll go back here, it's actually the check your learning part. So going back to calculating average atomic mass, we're going to do another example. And I suggest you do these extra examples when they give you an additional problem that says check your learning. You should probably do that as you're going through the chapter. And so here we're given 3 different isotopes for magnesium and their average percent abundance for the isotope and the masses for each isotope. And so we set up our average atomic mass just like we did before. We take our percent abundance, divide that by 100, or again, if you want to use a quick way, you can write it out as 0.7870 by just taking the decimal point and moving it 2 places to the left. Okay, so 0.7870 times 23.98. Okay, and then for the second isotope, same process. So 0.1013 times 24.99, or I wrote it out here, dividing it by 100, however you want to do it. And then the third one, same process, percent divided by 100 times atomic mass. So when you do the math in your calculator, here are the numbers you get. I wrote out everything. Okay, so when I added everything up in my calculator, this is the number that I got, 24.305713. And then I rounded to 2 decimal places. So here's a 5 there, so I went up to 31 there. Okay, so 24.31 AMUs. That's the answer I got for that question. Now, going back to our PowerPoint slide, we're going to do another example, example 25. So if we look at that question, just let me bring up here your textbook. It should be there. All right, so your example number 2.5, just here from your textbook. Here they're wanting you to calculate your percent abundance when they're giving you the average atomic mass and the masses for each individual isotope. So here you see that we have 2 isotopes for chlorine, chlorine 35 and chlorine 37. They give us the masses. They don't give us our fractional abundance. We're having to calculate that. Okay, so going back here to my document camera to show you what I did. So here's the information they gave us. Okay, they gave us the mass for each isotope. They did not give us our percent abundance. Okay, but they gave us the average atomic mass value. So if I look at my formula finding the average atomic mass, it's this thing here which we talked about earlier. So I'm going to substitute in my given information. So they gave me the average atomic mass, which is 35.0 453, and then they didn't give me the percent abundance, they gave me the mass. And so for the first percent abundance, I'm just going to call it X, chlorine 35 percent abundance or fractional abundance. Okay, so I'm going to call it X. And then for my second unknown, chlorine 37, I'm going to call that 1 minus X. Now, this technique is only really good if you're using two different isotopes. Of course, we are. But why 1? So if you think about percentages, if we added up the percent abundance for these two isotopes, because there are only two isotopes for chlorine, they should add up to 100%. Right? And so the value for 100%, not as a percentage, but as a fractional abundance is 1, right? If you take a percentage and convert that to some sort of decimal form of a number. So it's going to be 1 minus X. So whatever is left, right? So if this is 75%, then this would be 1 minus 75%, or 0.75. 1 minus 0.75 to give you 0.25, which would be 25%. All right, so 1 minus X. And then the mass for chlorine 37, which is 36.96590. Okay, so now here's our expression here that we need to simplify. So here we're simplifying this. Let me get a piece of paper so here we're going to simplify this. And so what we're going to do, we're just going to bring this number down, the average atomic mass, and then we're going to distribute this X. So 34.96885 times X is 34.96885 X. Okay? And then plus, and then now we're going to distribute this 1 minus X, this guy here. Actually, technically, it's almost opposite. In math, you see the number in front here. It's chemistry. And there's just this example. It's behind. It's okay. We're going to take this 36.96590, multiply it times 1. So we get that number, right? So positive 1 times a 36.96590, that's just a positive 36.965.96590. All right, and then we're going to do it again. So 36.96590 times a negative X is going to be negative, right? Because a positive number times a negative number is a negative number. So that's 36.96590X. Okay? So I simplified that expression a little bit by just distributing my masses to my expressions here with unknown values. So the next thing I need to do is to go ahead and combine like terms. So I have two different like terms here, okay, the ones with X's. And so what I need to do is I need to bring, notice here we have an equal sign, right? So I need all the X's on one side and all the numbers on the right. So what I need to do is what's called transposing, right? You learned this in high school. So here I have a positive 34.96885X. I need to bring it on the other side. So when I do that, it becomes negative 34.96885X, right? If you remember, if it's positive, I subtract 34.96885X to both sides, and it ends up canceling on the right side. On the left side, I end up with a negative value. Okay, that's called transposing. So if you need to review that, just go ahead and Google transposing or simplifying equations, and that should pop up. Okay, so I dealt with this number, this X here. Now I have another X that needs to go on the other side. I want my X's on the left and my numbers on the right. So here I have a negative 36.96590X. So when I bring it to the other side, it becomes positive 36.96590X. Okay, so I have my x's here. Now, here I have a number. It's on the right side of the equation sign, so that's good. I'm just going to bring it down. And then this number here is on the left, so I need to bring it to the right. And when I do that, the sign changes, right? So positive 35.453 becomes negative 35.453. All right, so now my x's here, I have a positive number, I have a negative number. Because a positive number is greater than the negative, it's going to be a positive number. So I take the difference of those two numbers, you get a positive 1.99705x. And then the difference here is 1.513. All right, so to solve for x, we divide both sides by 1.99705. It cancels on the left-hand side, but it stays on the right-hand side. And so after I divide, I get 0.7576. Okay, so that is my number, my value for x. Now I need to convert that to a percentage, so I multiply by 100% to get 75.76%. Now if you remember, for x, we define x as being the fractional percentage for chlorine 35, right? For chlorine 35. And then, so the 1 minus x is chlorine 37. So all I have to do is take 1 and subtract it by my decimal approximation here to get 0.2424, multiply it by 100, or because it's already in a percentage, you can go ahead and just take 100% minus 75.76, and that difference will give you the 24.24%, which is the percentage for chlorine 37. So our final answer here, chlorine 35, it's 75.76%, and for chlorine 37, it's 24.24. Okay. All right. And if you want to, you can look at your textbook. It also has the calculations here. It doesn't show you every step. I try to show every step as much as I can, so that way you know where the numbers are coming from and go through their math process. I know it may be a while. It may have been a while since some of you have done some math calculations. Okay, so going back to the lecture here, let me see. Here we go. All right, so we talked about calculating average atomic mass. We talked about calculating fractional abundance. We did that. Okay, so here are the examples we did already. So now we need to switch gears a little bit and talk about instrumentation called a mass spectroscopy or a mass spectrophotometer. And I've had experience using these before in grad school. They're very handy. I used it to double check my work when I did site-directed immunogenesis to confirm some mutations in a protein. In chemistry, though, we can use it to determine the number of isotopes and their masses for an element. And so that's very important to be able to do that. So with mass spectroscopy, the currents and natural abundances of isotopes can be experimentally determined using an instrument called a mass spectrophotometer. The sample is vaporized and exposed to a high-energy electron beam that causes the sample's atoms or molecules to become electrically charged, typically by losing one or more electrons. Then the cations are separated by their mass and charge. So here we see a figure that's showing you exactly what I just read about how a mass spectrophotometer works. So you have the sample here. It gets vaporized, okay, and turned into ions by the electron beam. Creates ions. The ions are accelerated, okay, and then subject to a magnetic field. And then basically, depending on the mass of the ions, they are going to hit at a certain portion of the detector. And so what you get out of this, when you inject your sample, you're going to get out some sort of a spectra here. And here we see a graph of the relative abundance of the isotope versus